Okay, so far we've talked about position versus time graphs and what we can see from about the motion from those position versus time graphs, right? But what about velocity versus time graphs, and what about acceleration versus time graphs, right? Is there anything we can learn about those graphs from the position versus time graph? And the answer is obviously yes, otherwise we wouldn't be talking about it. Okay, let's talk about it. So we have a position versus time graph here. And you guys can go to the slide that says position, graphs, and slope, okay? And we have a velocity versus time graph right here. And we have a acceleration versus time graph here, okay? Now, we are gonna specifically look at the one example where we have acceleration being constant and positive. Very, very simple example, right? And something obviously we see in life, right? Imagine a fish accelerating in one direction. Imagine a car accelerating in one direction. Imagine somebody, jumping from an airplane with a parachute, preferably. Okay, so here we go. In the case of constant acceleration, you get a concave up position versus time graph, right? It looks just like that. So something concave up, right? Now, remember what we said about velocity. Velocity is the slope of a position versus time graph, right? So let's look at those slopes. We have here a slope that's like almost zero, okay? Here, it gets a little bit bigger. Here, a little bit bigger. Here, a little bit bigger. So we should know that the velocity starts out almost zero, right? Gets a little bit bigger, gets a little bit bigger, gets a little bit bigger, and so you're gonna get a nice, straight, linear line for the velocity versus time, right? No big surprises there. We learned this in calculus, okay? Remember that velocity, because it's change in x and change in time, when you start talking about infinitesimal changes, you have dx dt, right? In other words, the slope, velocity is the slope of position versus time, okay? Now, acceleration has the same property. It is the slope of the velocity versus time graph, right? You guys maybe remember this from calculus also. Acceleration is just the slope of the velocity versus time, but since velocity versus time is just a nice line, what is the slope of a line always? It is a constant, okay? So you just get back that constant acceleration, we'll call it A naught. You just get back that constant acceleration that we started with that gave us this concave up position versus time graph, okay? Super, super simple. So a concave up position versus time graph gives you a positive slope velocity versus time, and you get a straight across over here acceleration that's a constant value. Okay, so let's take another example. Okay, we're going to take these same graphs, but I'm going to give you something a little bit more complicated. Okay, and I'm going to erase all this, erase all this, erase all this. Get that gone. See you later, buddy. Get this gone. See you later. Try to get these streaks. Man, I wish this technology had this power to just be like, and it just all erased. It'd be really cool. Maybe that's the next generation. So, okay, we have here a position versus time graph that looks like this. So basically it's doing nothing from 0 to 1. Right? Then from about 1 to 3, it's concave up, right? And then from 3 to about 8, it's a straight line. And then from 8 on, it's concave down, okay? So it's not perfect drawing, so rely on the slides, but that's roughly what's going on, okay? So the question is, what can we say about the velocity and the acceleration graphs from this position versus time graph? And the answer is obviously everything. We can solve it all. If you guys want to challenge yourself, go ahead and pause the video right now and see if you're right. If not, follow along with me. Between 0 and 1, what do we know? Well, the position isn't changing. If the position isn't changing, what do we know about velocity? Yes, velocity is 0. So from this point, we just get, from 0 to 1, we get a nice flat line. Okay, but during this chunk from 1 to 3, we have concave up. From the last example, what do we know about concave up? Well, the slope is getting bigger, 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 so the velocity must be getting bigger, 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 right? All the way up to 3. When you get to 3, it is a constant slope, so velocity should be constant. Velocity is not changing. Same slope, same slope, same slope, same slope, same slope, right? So that's going to be a constant velocity right over here, okay? Now, what happens here when we get past 8, okay? Well, we have the velocity having less slope, less slope, less slope, all the way to 0, okay? So in other words, the velocity should be getting less, 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 all the way to 0. So the velocity is going down. It's not negative, but it is going down, okay, all the way to 0. Okay? Do you guys see what we did there? Here, there was no change in motion, so no velocity, right? Here, it was concave up, so there must be a changing velocity. Here, the velocity is constant, so it's a constant velocity. Here, the velocity is decreasing, and then here, it's constant again, it's 0 at rest, okay? What does this say about the acceleration? Well, from 0 to 1, again, no change in motion, no change in motion, no acceleration. That's going to be a flat line right there, right? But in this case, when we get from 1 to 3 here, this guy is, the slope is a constant, right? Remember, acceleration is the slope of the velocity versus time graph, right? And the slope here is totally constant, which means we're going to have a constant acceleration. And it's a positive slope, so we're having a positive constant acceleration. So you just have this quick jump, it should be a straight line, jump to this constant acceleration, right? And then I make this line back down again, because here the acceleration is 0 because the slope is 0, right? Slope is 0, acceleration should be 0 here, okay? Acceleration is the slope of velocity versus time. Since the slope is 0, acceleration should be 0. Now we have, again, a non-zero slope, but this guy's negative. So you should get a negative constant acceleration. That is going to be a dip for a negative constant. This is a negative acceleration, and then it goes back to 0 after that, okay? So I hope you guys are starting to get the hang of this. We can always find the velocity and the acceleration if we have a position versus time graph to start out with, okay? Let's do one fun example. I will erase this guy, and sorry for the weird faces that I make every time that I have to erase one of these. Okay. All right, this one's about an armadillo. Is anyone into armadillos? I think they're pretty cool creatures, also kind of adorable. Also, one thing that most people don't know about them is that they can jump. So if you advance to the jumping armadillo slide, the question is, what would be the position versus time, the velocity versus time, and the acceleration versus time graph of a jumping armadillo from the moment it leaves the ground until it lands? Okay, guys, no big surprise here. We're going to do the same thing we've been doing. Start out with a position versus time, except this one's going up and down. So we'll call this y instead, okay? So the position versus time graph is going to be y, okay? Get that out of there. The velocity versus time will be beneath it, and then the acceleration versus time is after that. Okay. All right. So we have an armadillo jumping up and down. So it should start out with the highest velocity at the very beginning. Okay. When something leaps off the ground, it starts out with the highest, but then gravity starts to slow it down. It starts to decelerate, 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 decelerate until the velocity is 0, no slope, and then back down, back down, back down until it hits the ground, okay? Okay, that is the position versus time graph of a jumping armadillo. Okay, I'm not even gonna try to draw the armadillo. So what is the velocity versus time graph gonna look like? Okay, so here's what we know. Here, the slope is biggest. So here, the velocity should be biggest, right? Okay, next, we know here the velocity is 0, right? So here, velocity should be 0. And then here, the velocity is the biggest negative, right? So here, you're going to have a negative velocity. And if you just connect those dots, you could see that the velocity versus time graph for this armadillo is just going to be a negative straight line, right? It starts out with a high velocity, and then gravity keeps decelerating it until the velocity is 0. And then once the velocity is 0, it's accelerating it in the negative direction, getting more and more negative, until this final velocity here is the negative version of this initial velocity there. Okay? All right. Finally, what will be the graph of acceleration versus time? So, what do we know? We know that acceleration is the slope of a velocity versus time graph, and we know that as one hell of a negative acceleration, right? So that means that I drew this a little wonky because we need to make ourselves some room to make a negative acceleration. So if this is a equals 0, right, our line is actually some negative over here, some negative acceleration. Many of you will know that acceleration to be gravity, which is negative 9.8 meters per second squared, okay? So I'll just do that in a different color so it's a little bit more clear. Okay, so gravity, this negative 9.8 meters per second squared, is slowing this armadillo down after it jumps with some high velocity, slows it down to 0, creates a negative velocity, but the whole time that acceleration is that constant negative 9.8, never, ever, ever changes. Okay? Advance to the next slide. This is a video, and I put it in the module, and it's something called True Facts About the Armadillo. Now, I don't know if you guys have discovered the True Facts YouTube channel, but if you haven't discovered it yet, you're welcome. It is hilarious and informative at the same time, and is a great way to just go into a wormhole for about, an hour or half a day, who knows how long. And I will occasionally add a True Facts video to these lectures just because I think they're really fun, okay? In the next video, I'm going to dive into acceleration and explore exactly what it is and how to calculate it. In the meantime, have a nice day.